I don't know if this is working. All right, so red has the biggest wavelength. And you want to be able to write what I'm writing right now in purple. Big wavelength, small wavelength. So what does that mean about frequency? Max?
That the red would have a small frequency.
Small frequency.
And the violet would have a large frequency.
Large frequency. Okay, so this is something that you've got to either know because you understand it or at least memorize because you need it for the test. So if I say I need to compare the wavelength of yellow light with the wavelength of indigo light, which one has the smallest wavelength, what would you say?
Yellow.
Violet.
Wait a second.
What was your
Compare yellow and indigo.
So
which
yellow
one
has a
the
smaller
smallest?
wavelength than indigo.
But yellow is close to the big wavelength side.
I'm sorry, the larger,
Right.
larger.
So make sure that you're able to write this down, okay? Because when you think of the visible spectrum in this order, you have to think like big, spread out wavelength, and then getting smaller and closer together until they're like super duper. I can't even draw waves that close together, but right. And then out on this side would be things like heat and radio waves. Out on this side would be things like ultraviolet. That's what gives you a sunburn through, gamma and everything in between. But a lot of charts, like in your book, probably don't put things in that order. They usually go like the other direction on charts. So don't confuse yourself. Don't get confused about that. Our eyes have been designed to pick up certain wavelengths of color more effectively. So here in the middle of the spectrum, kind of on the green, the yellow side of green, this is what attracts our eye most readily. So you're more likely to notice something that's yellow-green than something that's red or purple.
Really?
Yeah. That's why they're starting to paint fire trucks like yellow instead of red now.
Oh. Mm-hmm. Oh, yeah, that's why they... What the heck?
Yep. So your eye is like more...
Contradicting every preschool book there is.
Yes. Your eye is very receptive to this yellow-green area. And so...
Green.
Yeah.
This is what eyes.
Yes.
All right, so when you look at a bright light and then you turn to look at something else, you still see the colors. Why is that?
Oh, that's called burn-in.
Oh, you mean like when you're like blinking, you can still see it right in your eyes, like if you look at the sun for a long time?
So I don't know how much your book talks about your eye particularly.
A bit.
But your eyes have rods and cones. Cones detect color. You have three types of cones that detect three major colors, which we'll talk about next week. And you have rods which detect light and absence of light. And so when you stare at something for a long time, especially something that's particularly bright or colorful, you get burn-in, where your rods for light or your cones for color have just been working so hard that they kind of go on autopilot like. And so then when you look away, you essentially have that image or light like kind of burned into your cones. And so they're still like firing as if they're receiving a signal when they're not. It's like a nerve mistake. So, if you look at something that's like the inverse colors, and then you look at something white, you'll see the picture in its proper color. And we'll talk about color addition and color subtraction next week. If you look at something for a really long time, it'll kind of burn that image into your rods or cones, depending on if you're looking at color or just light intensity. And they'll just keep going like they're still seeing it for a little while.
It's annoying.
Yes. Chris.
I saw like this commercial, I think it was like Liberty Mutual or something, and then like they go away and then you see like for a second it's like it's not even color, it's just like white. Mm-hmm. It's just like of the person that was there. No, that's You're mixing your
is
insurance
because-
companies.
Yep, and when you start driving at night, the headlights that are oncoming, will just,
Yeah, I've
and then
seen
you
that.
just can't
Annoying.
see after they pass, and you're like, oh, and that's when you don't want to hit a deer, so slow down.
So have another person in the car with
Do
you.
that. Oh, I didn't bring the stuff for the disappearing quarter thing. We'll do that next week. So, all right, speeds up, it bends away from the normal. Okay, so we looked at light bending. Strongly encourage you to really memorize that or have some technique to know it. And let's look through the study guide. So Jesse, tell me about the wave theory of light or particle theory of light or the quantum mechanical theory of light. Pick one and tell me.
What?
Like, how do we know light is a wave or a particle or something combined between the two? That's study guide question 2. Yes. Is that my phone? We just lay it there. Thanks. Here.
Wave theory of light. Waves gray of light.
Okay, Patrick, tell us. What do you think?
The wave theory of light views light as two transverse waves. The particles theory of light wave views theory of light.
Okay, light behaves like a particle in some circumstances, is what you're saying, right? And how about quantum mechanics? Quantum mechanics? How about the quantum mechanical theory of light?
Wait, what does it say about light?
Ryan? Quantum mechanical theory of light? Joseph?
It is where light is made up of packets of waves called photons.
Okay, packets of waves. So they take a little piece of both theories. Light is like a particle in that it is a packet, and light is like a wave in that that packet is made up of waves. Light does not ever have mass. None of those theories think that light has mass.
Why is that?
Because it doesn't. Like,
So you're saying light doesn't have mass because it doesn't have mass.
it just doesn't. Yeah. I mean,
If you were near a bright light and you were swatting at the light, wouldn't you
Shine a light at
kind
the
of feel
scale.
something?
right. I mean, the Earth is bombarded with electromagnetic radiation, both visible and invisible light, all the time, but we're not really picking up mass, except Earth sometimes gains mass from space dust landing in comets. Right. No, because to have the only way you can have weight is to have mass being affected by gravity. So, like in deep space, you would still have mass because you're made up of stuff, but you would not have weight because there's no gravity affecting you.
So not everything with mass is weight. But mass is everything that has weight.
Okay, so
Light.
yes, you would be very, very far away from
Your weight would be different
anything.
on the moon than if it was on the
Right.
Your mass would stay the same if you were on the moon, but your weight would be different.
Yeah, in deep space, yes, because
Weight
every object
is
in the universe is affected by the gravitational pull of every other object. But it would be pretty negligible. Yes.
So does light have volume?
No.
Oh my goodness.
I'm going with no.
Just broke his thinking.
So it's in another dimension.
No. It's in this dimension.
Nope.
You need Einstein to go any further, though. I've got nothing more for you on that.
That is hard to say.
Look
Yeah.
it up on the internet.
Don't believe what you read on the internet. Max. So, sound waves cause air to oscillate, or water to oscillate, or anything to oscillate. But what does light oscillate?
Light waves oscillate the electromagnetic field.
Good. And so we talked about general relativity a couple modules ago. Duchesne, what does special relativity tell us about the speed of light?
It's the fastest.
It's the fastest that anything that we know of. And there are some clever videos on the internet that talk about breaking the speed of light or getting things to go faster than the speed of light. And yes, they're clever little tricks, but there's still little tricks. So if you want to watch that, you could Google something going faster than the speed of light. Hank Green has a video that's sort of fun about that. So cosmic speed limit, and what else? Oh, the cosmic speed limit is the speed of light in
8,000 meters per second.
in a vacuum.
About air.
Air is a little slower, but we count them as the same for our purposes. Joshua, light is traveling through water and then it enters air. Does its speed increase, decrease, or stay the same? Yes, so light in air is faster than light in water. When it leaves water and enters air, the speed increases. So we're supposed to put these in order of increasing wavelength. So here's where my, I don't know what this is, but spatial skills or something break down, and I really have to think it through. So increasing means start with little things and go to big things. And I actually have to think that through before I make a mistake on a test. So if you're like that, really be careful. So from small wavelength to big wavelength, Ava. So violet, green, yellow, orange is the correct order. Violet has the smallest wavelength, and orange has the biggest in that list. And Elise, order the colors in problem 6 in terms of increasing frequency. Yep, so exactly the opposite. Because we know where wavelength is large, frequency is small, and vice versa. Jenna, do radio waves have a higher or lower frequency than visible light? Okay, so radio waves have low frequency, and then this is where it's really kind of important to have that electromagnetic radiation scale, kind of know where the visible spectrum is, what extends out past red, what extends out past violet, and then consider. So really knowing that little drawing on the board is pretty important for the test. So Jenna just told us that radio waves have a smaller frequency, bigger wavelength. How about X-rays?
They have higher frequency.
Okay, big frequency. So X-rays are out past ultraviolet, but not quite as far as gamma. And they have a bigger frequency. Lily, infrared light is given off by an object that's losing heat. Have you guys ever seen an infrared camera where maybe your head is red or orange, but your hands are